Hey guys, just a quick note. We're going to start in 2 minutes, so if you guys can take your seats, that would be great. Thank you. Okay, let's go ahead and get started, everyone. Thanks for coming. This is our end of year RocksDB meetup. So thank you for everyone from the industry and all our partners for coming out here to come and see what's going on in the RocksDB community today. My name is Danny. I am the engineering manager for the RocksDB team. I have the privilege of supporting the team. And I just wanted to do a quick welcome and some logistics before we actually get into the talks. So just from learnings from previous years, the one thing is on security, like please do not wander around the building. There is security that is cordoning off the areas that we're allowed to just wander in. So this area back here, and then obviously this room, there will be food later. You guys can hang out in these areas, but don't go wandering off. They will actually kick you out if that happens. So I just wanted to just give that notice right up front. Also, there's no smoking or vaping indoors or anywhere within the facilities, even if it's actually outdoors. For the actual talks, to just make sure that we stay on time, we're actually going to ask people not to ask questions. So I know there's a mic here, but we're not going to have time to actually do that. I'm just going to kindly ask people, if there are questions for speakers, please ask during the break. We will have a break at the midpoint, and then there's about an hour and a half of time afterwards for dinner and just to hang out. And so please go ahead and talk to people and ask questions there. If for people who are on Zoom, I know it's a little harder to interact, please, there actually is a meetup on the meetup.com page. There's a stream, there's an area where you can ask questions. And so what we can do is we can actually answer those questions asynchronously. Finally, there is a dinner and social time afterwards around approximately 6:30 to 6:40-ish. One of the things I do want to highlight is we do have vegetarian options available for people in the room who happen to be vegetarian. So we will have pizza, so just making sure that that's clear. And finally, I just want to give a caveat that the talks are being streamed internally and also recorded and will be uploaded on social media channels. So people in the room, there is a possibility that you will be, like your face, your back can be shown during this event. So I just want to make sure that people are comfortable with that, and I wanted to just give that notice. So so with that, yeah, I'm really excited. Welcome again. We have a number of exciting talks today from PingCap, Cloudera, Pinterest, University of Washington, also a number of internal talks from Meta. And so, yeah, well, let's go ahead and get started. So I wanted to introduce to everyone to Sunny, who is from PingCap, and he'll go ahead and give the first talk. Yeah.
Cheers. Hi, my name's, where's the cue thing? So it's about, can you hear me? Can you hear me now? Oh man, I feel like a American Idol singer now. Okay. So this is about TiKV, which is a distributed database. It started in 2015, and it uses RocksDB, which is why we are here. So I'm going to talk about the history and evolution of TiKV and why we started using TiKV, the good things and some of the things that didn't work, and also why we are moving away and writing our own LSM engine now for some parts of TiKV. So how many have heard of TiKV here? Wow, that's nice. And the remaining people will have heard it now. So next time will be better. Okay, good. So first, a little bit of introduction about myself, about the company, I suppose, how it all started. What was attempted as TiKV evolved, so it's a bit of a story, 2-3 slides there, and why we had to develop our own LSM storage engine for TiKV Cloud. It's a short talk, nothing technical, more hand-wavy sort of stuff. So it should be easy. So I work for PingCap. I do architect, which is like a generic term. I've been working on databases for a while, and I used to be the lead for the MySQL InnoDB team for, I don't know, 10, 12 years. So that's my background. Okay, so it started in 2014 end, early 15. And they were the founders of PingCap used to work for a company that was growing very, very fast. And so it was like the best of times. And because they were growing, they had to constantly add nodes and shard and handle all the data that was coming in. The data was huge. So they were constantly sharding and resharding the databases. It was almost a 24-hour job for them, and they were fed up with it. So they thought there must be something better. And the other problem they had was that once they would shard, the developers, when they moved to sharding, the developers would complain that they have to write their applications now with the sharding in mind. And they used to get annoyed. Why can't it be like simple queries like they did in the good old days? Then they found Spanner. This was one of the most exciting things for them. And they thought that they could write their own version of Spanner. And they were brave enough to attempt it. But one of the things was that Spanner wasn't open source. It required special hardware. And one of the things about PingCap's philosophy is that it must run on commodity hardware, so that you don't need anything special like RDMA or any of those kind of things. And they also wanted like an existing popular protocol like MySQL. And they were very familiar with MySQL, and they're big MySQL fans too, even till today. So this is the TiDB design philosophy that they came up with. They wanted a shared nothing architecture. Developers should not be concerned with sharding details because of the pain that they felt when they were managing large systems. And they said, no, that's something we couldn't live with ourselves, so we don't want to inflict that on others. Also, developers should be allowed to control where the data is placed. It shouldn't be out of their control. So they should have that flexibility, but they shouldn't have to worry about it by default. That was the other thing. It must use standard SQL. And also, it's the SQL engine that should determine the whole execution plan. It shouldn't be hints coming from the application developer. The SQL engine should do it. So they considered these things very important. It must have distributed transactions because now they wanted a full distributed SQL database. And they also initially wanted to provide flexible read consistency policies. In the end, I think currently we support only snapshot isolation. But originally they had more ambitious plans. And it must be highly available. This was their first attempt. So they tried all these engines initially, BoldDB, LevelDB, RocksDB, memory. And they had this, I think they got done in about 6 months. They had an SQL parser, an AST, an execution plan, and a KV API that mapped rows to a key value store. It didn't really work that much. Then they thought, okay, this is too slow, it doesn't work. And they were also big HBase fans. And so they were familiar with HBase, so they decided to use HBase in version 0.5. This was extremely slow. And HBase performance was, A was not good. Garbage collection was a huge issue. There was no native transaction support, and adding extra layers was causing more problems. And in order to run this, they had to have HDFS, Zookeeper, and all the other things, and this was something they didn't want. So then they came up with this. This is the current architecture of TiDB. So this is the storage layer of TiDB, basically. So it's stable API at that time. It was battle tested, used in very large installations. LSM was like a big thing those days. It still is, actually. It's write intensive, it's really good. Also, in a distributed system, it makes it really easy to move files around because files are immutable on disk, as everyone knows. So it lends itself to a very nice fit for a distributed database. So it works quite well. So RocksDB was and also compression was a big deal because by this time, they had customers who were in the hundreds of terabytes, and compression was a big deal for them. So this is like the TiDB sort of reference architecture. So you have the SQL layer, then you have the PD, which is like a metadata server, and then you have the TiKV nodes, which is a multi-raft, so which means, so if you look at, let's say, the nodes with the lines, so let's say the leader would be in node 1, and the followers could be in node 3 and node 4. Each of those, the region is, the name comes from HBase, the HBase origins of TiDB. But it's really tablet from Spanner. That's what it really is. So it's a bit confusing. It's unfortunate, but that's the way it is. And you can also add on a TiFlash, which is the OLAP side. I won't go into that. I'll just talk about the RocksDB part of it. So this is now the architecture of TiDB. It uses Raft for storage consistency. And it's row-based, OLTP. And so what's a region? So region is the logical sort of unit of TiDB. It's a tablet in Spanner. So whenever it needs to automatically shard, reshard, coalesce the regions, that is the unit that it deals with. So each region by default, I think, is about 96 megabytes. And I think that number also comes from, I think either Amazon, one of the papers from Amazon, I think, where they said that anything that takes about 10 seconds to transfer, and roughly, that's where it comes from. So it's easy to transfer across the system. All the traffic is also partitioned by region. So what that means is that your SQL queries are mapped to a region, logical to physical, and it deals with regions at the storage level. Think of this region as like a page, I suppose. So region by itself is not addressable from the SQL layer. The SQL layer only deals logically with keys. So the keys then go through the PD, which is the metadata server, to find the region. So that's why it says it's physically there's no clear boundary for a region. It's more of a container for the logical layout of your schema. One of the problems is that a few hot regions inside a RocksDB instance can start triggering compactions. And this causes a lot of jitter. And this causes a lot of pain, especially when you have very large databases. So in our TiKV nodes, each of those nodes is one RocksDB instance. So since this is a shared nothing architecture, each node could be in, let's say, 100 terabytes. And that's being managed by one RocksDB instance. And this causes massive problems in such large data sets. And I think as far as I know that at Meta, they deal in much smaller RocksDB instances because they call themselves, I think, small data engineers for this reason. Whereas in this case, it's just the opposite of how Meta uses RocksDB. So this causes problems in production. So what are the problems with this single RocksDB design that we have? It causes a lot of write amplification. There's just too much of compaction going on with these large instances. Latency jitter, which affects front-end loads. Customers complain. It lacks I/O isolation. So let's say you have some kind of multi-tenancy, multi-applications running on that TiDB instance. That causes a lot of problem. We can't separate reads from writes too easily. The other bigger problem is that the write throughput is limited. RocksDB seems to be designed for a more read-heavy kind of load because the way it relies on throughput and batching to reduce its latency somewhat. And it has a single writer thread. And this causes huge problems when you have very large amount of data going through RocksDB for writes. This is a huge problem for us. The other problem for us with RocksDB as it stands is that it's very slow for us to add a node and reduce nodes. It's a huge problem for us. The last points are to do with how TiDB works. So TiDB has PD, which is also like the metadata server, which does the mapping from the logical key to the region, to the physical location. So if you have lots of regions, the heartbeats become too much. And that's because we have a fixed size for these regions, so we want to come up with a system where we can reduce the number of regions by having variable size regions. It's not so much of a RocksDB problem, but it's the way the RocksDB is used problem. Oh, this is my old slide. I'll just go straight to the, OK. So these are the challenges that we are trying to address. How to improve stability at such large scale. Copying data, compaction, it slows down and causes problems. Indexing a large table, we have to have a trade-off between speed and stability. If we put all the resources towards indexing and doing these sort of things, it has a huge impact on our queries. How to take the scalability to the next level, because the data is just increasing every day almost. We also wanted multiple applications to share a single cluster, to basically multi-tenancy. They're not so much RocksDB problems, but like I said earlier, it's more to do with how we use RocksDB. So the thing is, when we try and do things, we have to do trade-offs. And each trade-off introduces a new configuration. That for this user or this customer, if you fiddle with it like this, it'll give you these characteristics. And that's something we don't want. We want our storage engine to work for all kinds of loads. And we also don't want all the complexity that comes with RocksDB. RocksDB is a very capable but very complex storage engine. It's not that straightforward. We also wanted to leverage the cloud infrastructure. So what does that mean? That means that you have things like S3. It gives you a lot of capability that in the past you would have had to write on your own and set up on your own. Very complex. It gives you almost unlimited throughput. Fine, it has some latency issues, and there's a cost balance that you have to figure out between the number of IOs that you do. So we wanted to use and design a system around these things that are available in the cloud. So that was one of the big important things for us. We want the elasticity that the cloud provides, scale, storage, and compute independently. Because TiDB, you can scale the compute and storage independently by design. So you can keep adding new compute nodes, and you can keep adding storage nodes. And we want to do that automatically for the users. They shouldn't have to provision for it. Hide the complexity of a distributed systems are probably the most difficult thing that at least I've ever worked on in my life. I have written a complete database engine myself. It pales in comparison to anything in the distributed world. It really does. It's a very humbling experience. And so if you push that complexity out to the users, it's not something you want to burden them with. You want to hide all that. How do you do that? And so the last one is, again, you want to integrate with all the other services that you find in the cloud. Make it easy to do all those things. Oh, shit. So we ended up with what's called the TiDB serverless architecture. So it's multi-tenant, disaggregated storage. So the primary storage is now S3. So what does that do? What are the benefits of that? So if, let's say, now I want to add a new storage node, all I have to do is fire up the storage node. It goes to the primary store, which is shared by everybody on S3. It uses a write-through cache, which could be local memory, local NVMe, or EBS, or whatever. Or even it could be a dedicated server that's acting like a shared memory cache. That's also possible, but that's a separate topic. So now you can have, if you have very large data sets, a lot of the data is cold. I read somewhere that it's 80% or 85%. So you can have all that lying in S3. It's much cheaper there. So with our TiFlash HTAP architecture now, both of them share the same primary storage. You don't have double the storage, one for OLTP, one for OLAP. Shared resource pool. So you can have, or we have, a pool of, what are they called, those, the nodes that you fire up. Like we have compute instances running, or storage instances running in a pool. And they can be shared between the system, between different customers. So the other thing, all these, the pool of VMs that we've got running, they can do compaction directly on S3 without affecting the front-end load. So the SQL node is running fine, the storage node is doing all the reading, and all the compaction is happening in the background by other nodes. So it doesn't affect the front-end load. Your DDL, large indexes over tens of billions of rows, all done in the background by separate nodes. So that's what this architecture. So in order to do this, we couldn't use RocksDB. I know that there is a new RocksDB disaggregated storage thing, but it's too late for us at least. This project was started much earlier. Also, originally we also used RocksDB for the raft log. So we removed that, and that is now a separate raft engine. And now that is the only write-ahead log, or only, let's call it the recovery log of the system. We don't log twice. We don't log into RocksDB, and we don't log into the raft engine log. So we can recover directly from the raft log. So RocksDB allows you to manually control the flush of the write-ahead log. I don't think it allows you to disable the write-ahead log completely. You still need it for recovery. But you can manually tweak it, manually control it. We don't need it at all. So that's reduced one whole class of writes for us. That was another reason why we moved away from RocksDB. So this is what the new architecture looks like. So you have a whole bunch of compute nodes. The resource pool I mentioned was all the separate VMs that are running, and they're on demand. They can start up, they can be used whenever they're required, basically. You have the storage is all on S3. There is a caching layer, which is a write-through cache, which I presume everybody knows what it is. And it could be anything. It could be memory, it could be disk, could be a shared machine even. That's what it looked like. That's what TiKV looks like now, and this is what the whole cloud without the RocksDB looks like. So you can see the mem table is written out to the local SSD, and then there's a write-through cache that goes there. You can have any number of nodes that can also access the same S3. Or it could be even different instance that is writing to S3 but doing its own thing. So it's given us a lot more flexibility that we didn't get out of the box with RocksDB. It's nothing against RocksDB. It's just not designed for the kind of use case for a database that we wanted to run. So these are all the remote services. And this is what basically we wanted our developers to see. So they should only be worried about transactions, indexes, schema, SQLY protocol. All the distributed side of things should be hidden from them so that they can have a happy life. And hopefully I've finished early. Thank you very much.
Hello. Yeah. Hi, Sunny. Thanks for the great talk. All right. Hi, everyone. Can you hear me? Yeah. So my name is Rajit. I'm part of the key value systems team at Pinterest. And I'm here to talk to you today about a massive project which our team completed at the beginning of this year to unify the different key value services we had at the company. So I wanted to take you through that journey and talk about some of the challenges and also some of the wins we had along the way. So quick agenda, I'll be giving a brief introduction about the team, talking about what the state of our key value services was in 2020, talk about how we did a pretty comprehensive evaluation of the database engines at that time, and then spend some time talking about how we did a very complex migration of hundreds of use cases across the company, and then share some results of this large project. So yeah, I want to give a huge shout out to the entire team who made this huge project possible, who I'm happy to be representing here. Cool. So let's get started. As I said, I'm part of the key value systems team. The team mainly focuses on low latency, providing low latency and high throughput key value services and real-time services in the company for basically all the engineering teams in the company. We've had a pretty long history with RocksDB. Our first RocksDB-based system was in production, I believe, in 2015. We've been using RocksDB in production since, and it's been a key foundational part of our real-time serving stack at Pinterest. So our team also built a real-time replication library called RocksPlicator, and it was open sourced in 2017. So RocksPlicator uses Apache Helix for cluster management, and it uses asynchronous replication. We use that to build distributed systems on top of RocksDB. So using this RocksPlicator and RocksDB framework, the team built multiple services across the years. A few of these are listed here. So RealPin is a service which was used for lightweight machine learning and ranking features. Counter, as the name suggests, is a service for maintaining counts of user actions across different dimensions and different time windows. Aperture was a system for tracking user impressions. And Rockstore was our key value service, which we built on top of RocksPlicator and RocksDB. So I'll be spending some time talking about Rockstore today. But yeah, so those were many of the services we had built. So our team supports a lot of mission-critical real-time use cases across the company. So if you're familiar with the product Pinterest, every time you visit Pinterest, most likely there will be tens, if not more than 100 requests being sent to our services. So the use cases supported by our teams span the variety of all services on the product, including home feed, search, shopping, and ads as well. We're also the storage system for a lot of machine learning recommendation systems too, and feature stores. Cool. So let's get to the topic of the talk. The year was 2020, and we realized that there were multiple key value services at that time in Pinterest. I've mentioned a few here, but there were at least 4 or even more key value services in the company. So there were Terrapin, User Metastore or UMS, Rockstore, which I just mentioned, and a couple more. So I'll spend some time going over each of these. So the first one was Terrapin. So Terrapin was one of the first key value services built in the company. It was based on HDFS. It supported only batch-generated data. So what that means is that the data which was loaded into Terrapin was generated using large MapReduce jobs and then ingested into or downloaded into HDFS-based systems to make them available for online or real-time serving. So it was based on HDFS. And the key feature supported by Terrapin was that it supported custom trimming of thrift fields. So at Pinterest, we have these massive thrift objects which are used to store information about the entities in Pinterest. And users were able to choose a subset of the fields they were interested in a large object. So Terrapin was useful in the sense that users could specify which fields they wanted, and Terrapin was responsible for actually parsing that thrift field and returning only the fields which were relevant to that user. So the next key value service is User Metastore. So as the name suggests, it was a service which was built to store metadata about the user. But over time, it evolved into a general purpose key value storage service at Pinterest. It was based on HBase. It supported strongly consistent and source of truth use cases. And the key feature here was that it had white column data format support, which meant users could store rows of data, but also could specify columns. It was still schemaless, so users didn't have to specify what columns they were storing beforehand. They could create columns on the fly, and they didn't have a limit on how many columns they could create. So the last key value store is Rockstore. As I mentioned, it was based on RocksDB and RocksPlicator. It supported both batch-generated and mutable modes. So batch-generated, as I mentioned, is where clients, they publish large amounts of data in their format. It's stored in S3. We convert that into SST files and then ingest them into RocksDB or Rockstore. So there are no real-time writes or replication involved in this. The mutable mode is the traditional key value mode you're familiar with, where there are live reads and live writes to the system. So Rockstore was initially built as the storage backend for a lot of machine learning use cases, which had very high throughput, but also had very low latency requirements. So that's why Rockstore traded off latency 4 consistency and durability guarantees. And it was designed to be simple so that it's highly performant. So that was the case in 2020. If you can see, so a lot of teams were maintaining and building these systems. There was high effort to keep all these systems running. They were using different sets of technologies, which meant we needed more expertise to optimize and to maintain these systems. There were no clear guidelines for application teams or clients who wanted to onboard a new key value use case. So it wasn't clear which was the best key value service to use, and clients spent some time figuring that out. And similar features were being built across all of them. So even though each system had its niche or it had its unique set of features which they were supporting, there was a huge overlap in the kind of features they actually supported. So a lot of the senior engineers across the different teams came together and kicked off a working group to figure out a solution to this problem. So what were the goals of this working group? So the first one was to align on the architecture of Pinterest's next-gen key value storage service, so that we have one single, if possible, one single key value storage platform for the entire company. Also finalize a roadmap to build out this platform and deprecate all the other services which were no longer needed. Another crucial point was that this design needed to be able to support the growth of the company and the growth of the business for the next 3 to 5 years. So how did we go about this process? So the first point was to collect pain points and survey the users on how they're using the different key value services and to stack rank the different functional and non-functional requirements. Then we actually did a pretty comprehensive research and collected data on different storage engines available at that time in the industry. So which are the popular ones, what features did they support? And we eventually shortlisted a bunch of candidates and benchmarked them against production and synthetic workloads. In the end, we decided on a final storage system. So I'll be talking a little bit more on steps 3 and 4 there about how we shortlisted the candidates and benchmarked the results. So we started with this big list of storage engines. You might be familiar with a lot of them. They were quite popular then and definitely popular now as well. Based on the user surveys and our understanding of how users were using our systems, we came up with a list of feature sets or features which we thought were important for the next-gen key value service. And we created a matrix basically of what features were needed and what features are supported in each of these database engines. It takes a lot of time to benchmark a new system, so we couldn't realistically benchmark each of these. So we took a combination of using the features as well as looking at the architecture of each of these systems to see which we thought would best fit our needs. And we eventually narrowed it down to 3 systems, Rockstar and UMS, which were the homegrown systems, and Cassandra, which kind of fitted the bill for a lot of the things we were looking for. So we did, even in our evaluation, we did prioritize systems which were more open source rather than proprietary. And even when you look at systems like DynamoDB, we didn't want to go with that because it would tie us to a single cloud provider, which we didn't want to do at that time. So we're down to 3 shortlisted candidates. So we spent about a month or 2 running benchmarking against all of them to get the results. So synthetic traffic testing, we did that with more than 15 workloads, varying in payload sizes, different kinds of traffic patterns, different sizes of the database. And we also had a lot of production workloads we could test against. So we made use of that to test some of these 3 database engines. So looking at the results, so on the x-axis, we have latency. So the shorter the bar, the faster the system is. And the y-axis is the different kinds of workloads we tested with. Blue is Rockstar, which is the RocksDB-based system. Cassandra is red. And UMS is the H-based system, which is in orange. So as you can see, for all the workloads we tested, we saw that the RocksDB-based Rockstar was performing much, much better than the others. I did want to mention a caveat. To get the best performance out of a database engine, you need to optimize it a lot. It takes months, if not longer. We did spend enough or considerable amount of time optimizing Cassandra, but we do realize that we could have done better if we spent more time. But we stopped at what we thought was a reasonable amount. So you can see latencies for puts was faster. Latencies was get was not too different. We saw Rockstar performing really well here as well. Even in terms of infra costs, we saw that RocksDB Rockstar was a lot cheaper and definitely more performant. This was from the fact that Rockstar used async replication. It didn't have quorum rights, a lot less overhead compared to systems like HBase. So yeah, the winner was Rockstar. So we were happy to be able to finalize this storage engine as the one we wanted to go for the future. So what were the recommendations of the working group? So we wanted to build a key value platform based on Rockstar, and we also wanted to deprecate the other services and migrate all the use cases from Terrapin and UMS to Rockstar. But at the same time, the team got together and thought, okay, 5 years from now, we'll be doing the same exercise. There might be a new shiny engine which we want to try out or which we want to migrate to. So how can we make it easier to do these analysis and evaluations and migrations over time? So at that time, the 3 different services I talked about, the applications were talking directly to the services, which meant the interfaces were very specific to the storage engine. So one thing we did with this effort was we wanted to build a unified serving layer, which we named as KV Store. And the key thing about KV Store was that its service or its interface was storage agnostic, which meant that applications would be talking to KV Store, and the storage engine would be abstracted away from it. When you have lots of hundreds of applications talking to a service, you obviously want to reduce any effort on the clients or the applications to use the service. So we didn't want client impacting migrations in the future. So this was one of the key design decisions we took at that time. So this was the KV Store architecture we came up with. Applications would interface only with KV Store, which was the stateless routing layer. And then KV Store used Rockstar as a backend storage engine. So in the future, if you wanted to try out different engines, you would just have that heavy lifting being done by KV Store. So the client to KV Store interactions wouldn't change. Along with this, we also built an export service for backup, to back up all the SSD files, and also to make them available for offline processing for any analytical use cases. We also built a metadata service to be able to track the different use cases and a UI for operations. Okay, so yeah, as part of this project, we had to build a lot of new features which were not available at that time to be able to absorb the different use cases from the other systems. As I mentioned, we built a service to offload data to S3 for analysis. We had to build a white column support into Rockstar, which was just a simple key value service. Had to add supports for read after write consistencies. As I mentioned before, Rockstar was initially built for performance, so we had to make changes to support things like stronger consistency, source of truth semantics, and we also ended up building a change data capture to be able to migrate some of the use cases from UMS or user metastore. So I have about 5 minutes left. Just wanted to walk through how we perform the migration from UMS to KV Store. Thought it'd be interesting to share since live migrations are always complicated. So how do you do a live migration of a database? So you first do double writes to both to you're writing to your existing system, but you also write to the new system. Then you backfill data from your existing system to the new system. You perform a bunch of validation or data validation and verification checks. You switch backends, and then you finally deprecate the old system. So if you look at this, and if you have an application actually talking to a service, then you'll see that the client or the application has to do a lot of work since they are the ones who need to do the migration. So to make this easier, and as part of this process, one of the main things we did was we decided to make UMS as a storage engine to KV Store, and I'll talk about this in the next slide. We used RocksDB's ingest behind feature to backfill data. So this helped us to ingest data, but not overwrite any of the updates which were done in real time. We used a combination of online and offline validation methods to make sure that the migration is safe to continue. So this was how an application would be using UMS as the key value service. The only thing we asked application owners or clients to do was to change their application to use the KV Store interface instead. So instead of the 3 steps I had mentioned before for application owners to do, all they had to do was 1 step. Instead of using UMS, use the KV Store API. And we did all the heavy lifting in the KV Store service to add UMS as a storage backend and do all the steps I'm going to be talking about now. So then we added shadow updates or double writes to the new system, which is Rockstore. We backfilled data from UMS to Rockstore, and then we switched, or in the data validation step, we did both online and offline validation. So in the online validation, we used KV Store to send a small percentage of requests to Rockstore to compare data. And in the offline validation, we took exports of both Rockstore and UMS and used cascading or MapReduce jobs to compare the data. Eventually, when we were happy with the results of the validation, we switched the backend, the primary backend to be Rockstore, but we still had shadow updates going to UMS. And this was, in case there were any issues, we could always switch back to UMS as the primary backend. And once we went through the period where we were confident that things are working fine, we finally got rid of UMS. So we saw great wins with KV Store or the Rockstore-based services compared to the HBase-based service. We saw KV Store was 2.5 times faster in terms of latency, 35% more efficient in terms of infra costs, and we also saw that it was much easier to scale the RocksDB-based systems, and we were seeing a huge, almost 50% reduction in KTLO effort and the number of production incidents. So yeah, one more thing about the wins. As part of this, we were able to complete the entire migration, deprecating Terrapin, deprecating Rockstore as a client-facing service, and deprecated UMS as well. So earlier this year, we were able to achieve our goal of unifying all the key value stores, and now we have one single key value store, which has RocksDB as the storage engine. Cool. Quick mention of the learns. So live data migrations are extremely complex. Be careful and validate each step before you move on. Making it easier for clients helps perform these large-scale migrations. The more work you put to application developers, it makes it harder. But at the same time, making it easier for clients means adding more overhead or more complexity for the storage systems. So yeah, here we are. So within a couple of years of building KV Store, we're having more than 1,000 use cases in production. We have an end-to-end latency at the KV Store layer to be about single-digit millisecond latency for most use cases. The scale is petabytes of data across all of these use cases and serving tens of millions of queries per second. And yeah, if you go back to my slide I mentioned before about the state in 2020, right now we have one single key value service owned by one single team. And we're seeing much better ROI in terms of how much effort we're putting in to be able to better a single key value service and make that the de facto storage engine at Pinterest. Cool. That was a lot. Thank you. That's my time. Yeah, I'll be here during the break as well. Please let me know if you have any questions.
Hey, we're actually running ahead of schedule a little bit, so let's have about 3 or 4 minutes of questions. So we have a mic. Does anyone have any questions that they would like to ask? Oh,
yeah. Yeah, hi. I'm Murli. My question is for the TiDB speaker. So I support one of the small data services at Meta. So I guess I was curious about some of the details or lack thereof in your presentation. You talked about RocksDB not scaling for some large use cases. Would you mind sharing with us some data so that we can actually fix any scaling issues on Rocks?
Where is Kevin? He's our storage lead, so you can give them some bedtime stories about the problems we face with the compaction from customers because of the large data sets that RocksDB can't handle because of its single write.
Yeah, it'd be great to start with some numbers, and we have a very active community.
I mean, I can give you some rough sort of hand.
Yeah, let's start with some.
So we have clusters that go up to, I don't know, maybe 900 terabytes. So because it's shared nothing, so the stuff is shared across nodes. So when, let's say you have a very massive write to a small section of your tables, it causes a lot of write from the mem table to the disk, and then that tends to trigger a lot of compactions. That brings the entire thing down. Whereas for you guys, you have lots of small instances, right? So if compaction kicks in for a system, it's isolated. For us, because there's one instance of RocksDB, I think it has an impact of 10% or 5% on the foreground SQL queries when a node goes into the system goes into compaction because it's shared across. So we are talking in terms of hundreds of terabytes, not one terabyte.
Per RocksDB instance.
Per RocksDB instance, that's the problem. And RocksDB is not designed for that, from what I can tell.
Yeah, so it'd be useful if we can engage offline and try to figure out scaling
if you guys can help us, why not? That would be great. Thank you.
Do you have any other questions? There's one.
For the Pinterest talk, I was just interested in any additional information you can give about how you did the data validation between two different storage systems offline and difficulty in having a consistent view between those two systems offline.
Yeah, that's a great question. It's always hard to get to a state where both systems are entirely or exactly the same. So we used in the offline mode, you would export the data from both the systems, compare them. You would have timestamps, and you would try to reduce that delta between the two systems as much as possible. And in the online validation was simple. You have X percentage of your traffic comparing data between the two systems, and you reach a threshold of 4 nines of accuracy to be able to call it done. So does that answer your question? It takes a few rounds of iteration. So you compare systems, but there are obviously real-time writes going through. And since they're two different systems, the way timestamps are handled are different. So there's always that delta. So you keep iterating and running these offline validations and fixed jobs to kind of get them to a state where they're converging.
Okay, so it was afforded by a combination of the fact that at the application level, or in how you choose the data that gets stored into each system, that there are timestamps with each record, so you can use that to compare offline, and also not striving for 100% perfection.
Yes. Yeah.
Okay.
Yeah.
I think we have one more question.
Yeah, this is Ramesh here again.
Yeah.
Since you mentioned that you unified, all the company information to just one distributed system, did you face any problems like they did? Like they had multiple terabytes of data trying to write to smaller places, and then did you have any threshold that beyond this you need to scale up multiple DBs or something like that?
Yeah. So the way Rocksplicator works is it handles sharding, and I think it's a similar concept of how Meta uses it. Is each shard of the database is a single RocksDB instance. So you could have a use case which is hundreds of terabytes in data, but as long as you overshard your database, your single shard size is a few gigabytes, or maybe up to 100 gigabytes at max. So with that, maybe we're not seeing the same problems as PingCap or TiDB does. But we do see issues with larger shard sizes because of the way when you need to fail over a leader, or when you need to move shards, it takes longer. And the one thing which we aren't doing right now is to dynamically reshard a data set. So
Okay.
that's something we're looking into, but it's hard. It's difficult with our current design. But with us, we have figured out workarounds where we overshard a data set from the beginning, so we don't run into these problems.
Okay, so from the beginning, keep it large. Okay.
Yeah.
Okay, cool. Thanks.
You can just leave the mic.
Okay.
I got a question to the printer.
Okay. All right. Let's go ahead and go with the next talk. So yeah. Oh, just one quick thing. Like one of the reasons I love these meetups is we get to hear about both the benefits of working on RocksDB and also the challenges that people have. So I love sharing this information and being able to collaborate together. So yeah, Sunny, I'd love to chat with you afterwards, and when our teams can chat, we can understand challenges that are there, and we can definitely collaborate there. Yep. Cool. So yeah, let me just introduce myself again. I'm Danny. I have the privilege of being the EM of the RocksDB team and supporting a great set of folks that are at the bottom of this slide. And so I will be sharing on behalf of the team a little bit about our vision expansion and updating on what we've been working on over the past year. So before I go into looking into the future, I did want to take a quick retrospective on how we actually got to where we are today. And so from that perspective, I wanted to start first with the RocksDB mission. For those of you that aren't aware of this, this is a mission that we've had for quite a while now. We think that it's still relevant today. I'll just read it out to you. It's a fast and easy to use storage engine for any workload and any hardware platform. And so from that, when you actually look at the RocksDB storage engine, and this is one of the slides that I personally am really proud of, and I know the team is also really proud of as well. You'll see that they're among the companies and technologies that actually leverage RocksDB. It's a veritable who's who in the industry. We have major, the people that are presenting today, and a large number of influential technical partners and companies that all actually have RocksDB as one of the fulcrums of their infrastructure. And the reason why is because, and this, one thing to say, this is just a slice of actually the companies that are using us. There's many more that, we couldn't put on the slide, but it's just something that we're really proud of. And so for those of you who don't know, we actually are celebrating our 10th year anniversary of RocksDB this year. And so because of that, what I did is I actually went on and searched through some academic articles and looked at some of what other companies have said about RocksDB. And you can see a common theme emerging. And it's basically that RocksDB is an industry standard, it's a de facto standard, or it's a go-to choice as a storage engine, an open source storage engine for the industry. And so even for companies that aren't necessarily using RocksDB, if they built something themselves, they actually validate that what they built is actually usable and performant by benchmarking against RocksDB. And the reason I really wanted to highlight that is, as I look into the audience here, there's actually a number of people that are old RocksDB engineers, old RocksDB leadership, who come back to these meetups and continue to contribute to the community and meet with us. And so if you think about like what is the bedrock of a good performance storage engine or any sort of system, you think about reliability, there's stability, there's high performance, and there's code quality. And these are kind of the pillars of what any solid system is built on, or solid storage engine. And from that perspective, like we really stand on the shoulders of giants here. From Dhruba, who originally founded RocksDB, to the original team and members in this audience who used to develop internally at Meta for RocksDB, or partners who have submitted PRs through our open source systems. This is a collective, like what we just shared about, where RocksDB is actually the storage engine of choice in industry. It's not something that is just an accomplishment from within the team, but because of everybody's efforts within this room. So I wanted to just take a moment and just really acknowledge that, and just something that we're really proud of. Also, highlighting some of the production-ready features that we've delivered recently, maybe in the last year or two, in case people aren't aware. There's a number of new features that we have, such as the next evolution beyond Bloom filter and ribbon filters. We've moved from an LRU cache over to a hyperclock cache, where we vastly reduce any necessary locking, almost no locking at all. We have better data model support with wide columns. We can support large values much more efficiently with blobdb. We have enhanced memory tracking, so you're aware of what is your memory usage, and we bucketize that for you. We've improved range deletions, and we also, this was mentioned before, we have this new paradigm where we actually have disaggregated and tiered storage in production at Meta at huge scale. And so, touching on that point, from the last RocksDB meetup, we actually presented this. This was a paper that was accepted at SIGMOD, a highly prestigious conference, where for the first time, we're actually able to run RocksDB as a storage engine and as a library in a disaggregated fashion, where we can independently provision both storage and compute. And so this helps us realize a vast array of types of efficiencies that weren't possible before, allows us other types of efforts such as remote compactions, secondary instances, read scaling. And so these are all really exciting things that we can continue to invest in the future. And so now that we're done with the retrospective, the question comes up, like, where do we actually go from here? And so from that, when we thought about that, what happened this year is that the RocksDB team, we had an offsite, and we kind of challenged ourselves. And we said, if we took some time to dream, let's assume that there's no shackles, there's no limitations on what we can do, what is realistic or not, we don't have to necessarily worry about that. Let's just think about what we can actually accomplish when we think about the next 10 years of RocksDB. And we don't want to constrain that in any fashion, right? We want to think about where our vision is going to be 5. It's not just 1 or 2 years from a tactical standpoint, but we want to think about where are we 5 or 10 years down the road. And so I wanted to share this quote. Like, this is the quote that was shared with the team. It says, "If you want to build a ship, don't drum up the men to gather wood, divide the work and give orders. Instead, teach them to yearn for the vast and endless sea." And from that perspective, this is what the team challenged ourselves and say, what can we do to yearn? Well, how can we make ourselves excited to continue to innovate in the storage engine? And so I wanted to share that with this group today, because I'm hoping that as a community and as with many of our industry partners who continue to help invest in RocksDB, we can actually do this together, right? Where do we see RocksDB innovating 2, 5, 10 years down the line? And so we want to move from a tactical approach to a strategic approach here. And so based on that, I wanted to share about some of what RocksDB as a team internally at Meta, what we're thinking about for the next 3 to 5 to 10 years down the timeline. For those of you who are not aware, at last year's RocksDB meetup, we actually presented an updated vision. And from that vision, we actually talked about what are the 5 pillars that we are going to invest in for the future. And so you have them here. I'm not going to list them. But I wanted to focus more on the ease of use and new data model. And so what came from that is when you actually look at the RocksDB vision, and we actually thought about, does it make sense to adjust the vision? Do we need to change it? But the team felt that it was still relevant for today. And there's 2 parts that actually really stood out to us. One was RocksDB being easy to use and for any workload. And so if you think about RocksDB being easy to use, for those who have used it in production, I do think that once you have it up and running and there are many knobs to configure it, but once it is up and running, it is very reliable, it is very performant. But getting to that point may not necessarily be easy because of so many configurations, and that the fact that we support quite a few workloads and use cases internally and externally. It does take some time to actually make sure those knobs are aligned in the right way to support the traffic patterns and the workloads that we need to support. And so we thought about, can we actually make it easier to use? And I want to quickly caveat this by saying the goal is not that we are the easiest to use storage engine. There are other engines out there that are quote unquote easier to use because they are tightly coupled to a specific use case. And in those and when you think about RocksDB, we're not coupled to any specific use case. We are a general purpose storage engine. So we have to make intentional trade-offs of, what kind of design decisions do we want to surface? What are our APIs like, so that we can support a wide array of use cases? But because of that, we intentionally will never be the easiest to use storage engine. However, can we become easier to use? And I think the answer to that is yes, and I'll share some more details. For any workload, I wanted also in a few minutes I'll share about how some of our efforts in integrating with other libraries of some of our AI and ML efforts, how we think that we can innovate in that area. So let's go back to easier to use. There are some things that are quite obvious and simple, and that we definitely should invest in. So the first thing is, we want to make sure that any API that we have, and the API as it evolves, is very clear. I think that's the baseline of what we can do. In addition to that, we want to make sure that the documentation that we have is high quality, so that anybody, external partners, anybody using it can understand how to use our library and our storage engine. Now, where it becomes interesting is we want to minimize the need to control RocksDB internals. So if we move from a white box to a black box approach, can we actually reduce the surface area of tuning that is required? And can we be intentional about it, but actually have some good balance as well? And so from that perspective, we thought about, like, does it make sense to actually invest time in a auto tuning and healing approach? And in the long run, probably not in any near-term future, but should we use tuning advisors? Should we actually build one ourselves? What are the external tuning advisors that are out there? I think you'll hear a little bit about what is in the industry with the University of Washington talk today. So from the perspective of auto-tuning, there's quite a few things that we can actually do here. But the high-level point is, like, we want to be able to apportion our allocated resources for different purposes, or save the allocated resources for later when they're more useful. And so, for example, like, can we have good heuristics to actually internally to achieve these objectives? And so, if we actually think about some of these subjects, and I'm not saying that we're fully committed to doing all these things, but I want to, again, kind of dream a little bit and give you an example of what we're thinking about. But for example, scan auto-tuning, and Akanksha is going to give some of a talk later on some of our efforts on this. But can we actually be able to prefetch data in a way to reduce IOPS and reduce IO? And can we do that intentionally at first, and then maybe have the system do that automatically and auto-tune itself later? For compaction threads and throughput, right? Is there a way that we can reduce interference with foreground traffic? Right? If we think about auto-tuning, can we make sure, like, can we tune the number of threads? Can we tune our throughput automatically without the users having to statically set those values, so that it can dynamically adjust without any human interference needed? For the memory budget allocation tuning, so some examples on that is that we don't want to fall behind when mem tables build up and cause write stalls, right? And so would we be able to let the mem table, for example, eat into the block cache memory and be able to evict blocks from our LRU cache in order to be able to tune the memory budget a little more intentionally? Another idea that we had is, for those of you that are familiar with the compressed secondary cache, can we actually auto-adjust the ratio between the block cache and the compressed secondary cache, so that if we understand the particular signatures of the traffic workloads that we have, that we can adjust that and be able to, again, prefetch data, and when we're evicting data, we can potentially put that in the compressed secondary cache with a acceptable CPU overhead without having to go and use disk again. And so also with peak versus off-peak detection, are we able to understand when traffic is high and learn when traffic is low? And for example, when traffic is low, perhaps we can run some of our lower priority compaction jobs and make the system continue to be performant, and not have compaction affect our workloads as much. And we just talked about some of the challenges with compaction, and so this is something that we can potentially look into. Again, these are all ideas that the team is really excited about and that we will be investigating for the future. For the data model evolution, in many ways, most partners internally, externally use RocksDB as an opaque key value store. RocksDB itself doesn't necessarily understand the keys and the values. It's a sequence of bytes. But if we actually adjust it, and can we actually understand what the structure of the keys are and the values, for example, through wide columns, so that we can optimize and be able to provide other types of efficiencies and paradigms and things that we aren't able to do today. So from that perspective, like some of the efforts that we're going to start investing in is for those of you who are not familiar with FACE, it is a very prominent similarity search library that is actually open sourced by Meta. It's kind of the de facto standard today. So we have an effort ongoing where we're going to work with our service partners and partner together to actually implement the FACE interface. And this will help us as data spills over. When you're thinking about storing large vectors and inverted lists within using the FACE library, if that data spills over onto disk, can RocksDB actually store that in a way, understanding the structure, so that we can help out with the similarity search, the KNN similarity search algorithms, or we can potentially store it in a way that we can retrieve it quicker and even push down some of the predicates. Like when you're doing the filtering and the searching, can we actually help out with that so that the data that returned is a smaller subset than what is originally there for efficiency purposes. For CacheLib, for those of you who are not familiar with CacheLib, it's also a very prominent open source library. It's a high performance in-process caching library that is thread safe. And it's a team that we work closely with. They actually back our flash-based secondary cache at Meta. And so can we actually work with them to understand how can we actually do caching in a more intelligent fashion, again, in a way that can potentially reduce disk IOPS. And finally, we also want to think about supporting diverse workloads. As we, there's other cases where we can help out with analytics use cases, supporting potentially some of these HTAP workloads where we combine the OLAP and OLTP use cases together. And then also with some of the columnar abstractions, just as an idea, does it make sense to tee traffic off that is coming into RocksDB and build out some of these Parquet and ORC columnar files so that we can support some cases of columnar or analytics use cases in a way that we can keep the data as fresh as possible. So I just talked about a lot of really exciting opportunities. I hope that is exciting some people in the room. But I also wanted to be realistic. There are a lot of challenges ahead of us. So number one is we need to have a mindful balance of innovation and stability. Right? What got RocksDB to where we are today is that we are very reliable, we're rock solid, and we are very predictable in our performance because of all the hard work that we mentioned the people in this room and the team has invested in. And so we don't want to trade that off in the name of innovation. At the same time, we do want to innovate. We want to think about how we can go into new types of use cases in accordance with our partners and working together hand in hand with them internally and externally. But it's just something that we have to be very careful about, right? We don't want to lean one way or the other. The other one is like, everything that I mentioned, they're non-trivial challenges. When you're thinking about auto-tuning, when you're thinking about supporting AI ML use cases, these are not easy problems. They're really, really hard, and success is not guaranteed. And so, I guess like a famous NBA coach said, everything you want is on the other side of hard. So from that perspective, I don't see it as a bad challenge. I see it as a fun challenge. It's something that the team is excited to tackle. And finally, the successes will outweigh the failures. Like a lot of what we talked about, probably, a good number of them may not come to fruition, but some of them will. And I do believe that the ones that do come into fruition will actually will really support and benefit the industry as well as Meta for many of you guys, and outweigh what doesn't come to fruition by quite a bit. So yeah, that's the end of our vision talk. I wanted to thank you again Please come join us. Join us on this journey. You guys are already here. And finally, a last plug. We are on Threads now. We do have RocksDB_OSS. So go ahead and follow us on there. Okay, we are at the midpoint of our talk. So I'm going to give a 10-minute break now. So it is, let's see, it is 4:20 or 5:20. So let's come back at 5:30 and we can continue the talk. Thanks, everyone. Hey guys, it's been 10 minutes, so let's go ahead and take our seats, and then we can go ahead and start with the next talk from Cloudera. So if you guys can take your seats, that'd be great.
I'll just be here whenever you call me.
Cool. All right. So up next, we'll have Prashant, who's going to talk about RocksDB checkpoint diffs. We're going to follow up that with a talk from Akanksha, one of the engineers on Meta, and then we'll close with a talk from UW. So Prashant, go ahead.
Thank you. Hi. I will start with the introduction. My name is Prashant. I'm an architect for the storage platform at Cloudera. And then I have my team here with me who has been working on this feature. So this is the agenda of... Yeah. So this is the agenda of the talk today. So first, I'm going to talk about Apache Ozone, the product that my team is working on, and then how it uses RocksDB. And then I'm going to talk about, why do we need a RocksDB checkpoint feature in the first place? Where is RocksDB utilized in our Ozone architecture? And then I'm going to talk about why do we need the checkpoint diff mechanism, something that is not available in RocksDB today. And we will go, a little bit in depth into what is the diff mechanism, how exactly it works. And if the time permits, we will have a small demo towards the end. So Apache Ozone, it's a scalable object store for, it was primarily designed for big data workloads. It was designed by the same set of folks who were, involved in the early design of HDFS itself. So we have a bunch of customers in Cloudera who work on like really big HDFS clusters. We are talking about like 5,000 node clusters and so on. And HDFS has been around for like close to 16, 17 years. It has seen its scalability limitations. So the moment you want to cross like more than 200, 300 million objects, the moment you start crossing several petabytes of data storage, it starts seeing problems. And then this is where we designed this Ozone object store. It is easily scalable to exabytes of data, billions and billions of objects. It does not have any problem that you have seen with name node, like the problem with restarting or HA. So all the different components of Ozone, architectural components of Ozone, they have inbuilt HA. All of them run raftering for all kind of updates. It's a very strongly consistent object store. It was GA'd back in 2020, so it's pretty stable at this point of time. And it comes with all the standard features that HDFS used to offer, like replication, HA, security, EC, ACLs. It's fully integrated with all the different compute engines like Impala, Hive, Spark. And on top of that, it's a growing open source community. Of course, Cloudera has an investment in Apache Ozone, but then now we have different community partners. We have G Research, Tencent has contributed a lot, DD, and so on and so forth. Like bunch of them are coming on board now. And today's state of Ozone, it's operational at scale. We have customers who are trying it. Now, where do RocksDB fit in Ozone? So for that, let me give a brief, bird's eye view of Ozone architecture. So this is how your Ozone cluster looks like. So those of you who are familiar with HDFS, it was pretty straightforward. There was a name node, and there were a bunch of data nodes. And name node used to become a single point of failure, right? And it used to become bottleneck. So what we did was clear separation of tasks. There is a Ozone Manager component that is responsible for namespace management. There is a SCM component that is responsible for your block management layer and cluster membership. And then eventually you have data nodes that hold the data blocks. So all block allocations or the cluster membership, it's driven by our SCM component.
And other than that, we have Recon and Ozone Console. This is for diagnosability, observability into your entire cluster, exactly what is happening. Clients have different options of either coming through the HCFS, that is Hadoop compatible file system interface, or they can come through the S3 interface. So if you have applications that are already running on HDFS or S3, you can seamlessly migrate to Ozone. Now this is where RocksDB comes into picture. All of metadata that is maintained by all of these different components, finally we store it on RocksDB. Now why do we need RocksDB checkpoints? So key driver for this was a new feature that we developed for Apache Ozone Object Store. So today, I believe Apache Ozone is the only object store out there that supports this snapshot functionality. Other guys out there, they support individual object versioning. They call it a snapshot, but no, that's not a snapshot. So in Ozone, we offer snapshots at bucket level granularity. And snapshots in turn itself enables multiple use cases for our customers. You know, you guys are in a storage industry. You are aware of like bunch of these use cases. So just what this feature is at a glance, right? So if you look at Ozone namespace, at the topmost layer, we have volumes. I'll come to that. Within volumes, you can create different buckets. So buckets in an object store, this is what you are familiar with AWS S3. On top of bucket abstraction, we have volume abstraction. So if you are coming from the HDFS world, you can think of volumes as different federated namespaces. One more use case for volume is in a multi-tenant environment. You can isolate different namespaces for different customers on different volumes. So this snapshot feature that we are providing, it operates at bucket level. So here is an example. You take a snapshot at this bucket, and then you can continue to access it just like your active object store. You just need to prefix it with .snapshot and particular snapshot ID prefix. So this is how it works. And of course, when you are creating different snapshots for your object store, it needs to be efficient. We are talking about an active object store that's going to contain billions of objects. It's going to contain petabytes and possibly exabytes of data. And every time you create a snapshot, you don't want to lock down that much space. So a snapshot only need to use the incremental amount of space, right? Here's an example, right? Again, if initially you have 100 gig of active OS logical space, actual physical space is also 100 gig. But when you create a snapshot, right, even though your logical space is 200 gig, all of it is shared. So you only need physical space of 100 gig. And as you delete or add data, that's fine. You only use the incremental amount of space. Now, how does Ozone Snapshot leverage RocksDB checkpoint? So for that, we need to take a closer look at Ozone architecture. So earlier I talked about it has 3 major components. One is Ozone Manager that is responsible for managing your namespace. In the namespace, for a given key or a given file, it's going to maintain a mapping of all the different blocks where you can find the data. So in this case, you can see that key 1 is can be found at containers C1 and block B1. So what is a container abstraction? In Ozone, we don't track data location with just blocks. We have broken it down into container abstraction, storage container abstraction, and the block within that container. So containers can track about like 5 gig in size, and within those containers, you can allocate individual blocks that can be about 128 or 256 MB. The advantage is when the data nodes are sending reports to your cluster manager, which is storage container manager in our case, it's going to be concise. So at storage container manager level, we don't track individual blocks, unlike HDFS. We just manage and maintain different containers, which are bigger units. So coming back to this location, right, C1, B1, from SCM, I know that this container C1, it can be found in 3 different data nodes, 3 different replicas, right? And once I know which data nodes to go to, I can locate the blocks. So this is how client interacts, right? So one important thing is in data node, whatever you write in your containers, it is immutable. If you want to update any object, you have to write it in a new place. And we take advantage of that when we create a snapshot. So this part is immutable. I don't need to take a snapshot of this one. Whatever is maintained by storage container manager, it's a metadata that can be rebuilt based on the container reports that we get from individual data nodes. If I snapshot my namespace that I'm managing in Ozone Manager, that's going to be good enough if I want to take a snapshot of my entire cluster. Well, not there quite yet. I also need to make sure that my deletion logic, it's not going to reclaim any data block from individual data nodes if it's referenced by the Ozone Manager or any of its snapshot. Once I take care of these things, my feature becomes easier. But then, for implementing a snapshot, I need to go a little bit deeper into this. So if you look at Ozone Manager, how it maintains namespace, it's going to maintain it in RocksDB, right? And Ozone Manager itself runs a raft ring. So that is how it makes sure that all the different RocksDB database instances, they are going to be consistent with each other. So a little bit more into details. So if you look at a bunch of operations that are client operations that are arriving in Ozone Manager, then this is how it's going to look like, right? It's a series of transactions. And raft log, it's going to make it sequential, right? It's a bunch of operations. If you replay it in exact same order on all the different Ozone Manager nodes, you are guaranteed that your data, RocksDB database instances that you are managing, they will be consistent. Now, how does it work? I'm going to divide it into different batches. The moment I see a create a snapshot operation, it becomes a sync barrier. Everything before that has to be committed when I create a snapshot. Ultimately, if I look inside the RocksDB directory, I will have a bunch of SST files, right? So moment I see the create a snapshot operation, I'm going to create another snapshotted directory. This is where I will leverage the RocksDB checkpoint feature. And I'm going to create a hard link to the existing files. And this is how I will end up sharing all the space. Any new modification, they can keep going to the original active object store RocksDB directory. All new changes, in this case, they can go to 4.sst. So this is how, like in a nutshell, at the very top level, that is how my snapshot feature will work. Some of the key points, right? It's when I see the create a snapshot operation, I flush the wall. I create a checkpoint in a different snapshot directory. As a result, I get instant snapshot. So we tested it on our system. Even if my object store, it contains few billion objects, I'm looking at a snapshot creation operation that is in single-digit seconds. And all snapshots, they are self-contained with hard links in an independent directory. And we use Raft. We have an implementation of Raft called Ratis. That is what we use for providing consistency. So all the nodes that are running Ozone Manager, they have the exact same notion of at what point the snapshot was created. Now, why do we need RocksDB checkpoint diff? So for that, let's look at one of the features of snapshots. It's called snapshot diff. What it does is, given 2 snapshots, it can very efficiently compute diff and tell you what has changed. And the amount of time it takes to compute this snap diff is proportionate to the amount of churn. So even if your, let's say your active object store, it contains, let's say, 10 billion objects, but between 2 snapshots, if you only change 10,000 keys, the amount of time to calculate it would be proportionate to only those 10,000 keys. And of course, it's designed with, for an object store that's going to hold billions and billions of objects. It's something that can track, churn of several million objects between any 2 snapshots. So we designed it to have a synchronous API. And the response that this API returns is paginated. with continuation tokens. So this is how your snap diff is going to look like. Now, in order to implement this, right, so we use RocksDB checkpoint for implementing snapshot, but what about snapshot diff? RocksDB does not provide any such functionality, right? So we added it. Oh, before I go to that, so this is one of the use cases for your snap diff computation. So the very first thing, if you have a DR use case, the very first thing you will do is you will take a stable image with the help of a snapshot. And this stable image, you can replicate it to the remote site, right? But the remote site replicate has to be maintained, pretty much in sync with your primary site, because you want to provide a very good RPO, right? So this is where delta replication comes into picture. Again, the same picture. At time T1, I took first snapshot. At time T2, I took another snapshot, right? So I have already replicated the snapshot T1 on the remote side. I got another snapshot at a different time. I don't want to fully replicate it. So what I will do is I will make use of this snapdiff API. I will compute it efficiently. I'll only take the incremental changes to the remote side and apply it there. And that is how I arrive at the exact same image on the remote site as well. So now let's look at how exactly the snapshot diff works, right? So for that, what I need is I have got 2 checkpoint directories within RocksDB. I want to very efficiently identify what has changed. So what I do here, so this is the mechanism, right? In RocksDB, you have a write request, your active mem table gets full. This is when you create your SST files, right? Over time, you will have a bunch of SST files. So what we can do is we can just compare the SST files. So when I took a snapshot 1, I had 1.sst and 2.sst. When I took, then you got some new updates. And then in your snapshot 2, you have 1.sst, 2.sst, 3.sst, and 4.sst. So if I wanted to identify what has changed, I'll just look at the incremental SST files, right? And that's going to give me time proportionate to what has changed. So this all looks simple. Not there quite yet. What about the RocksDB compaction? Yeah. So for RocksDB compaction, we track RocksDB compaction. So we have registered listeners for all the different events that RocksDB sends when it does compaction. And based on that, we can build a map of what has happened. So this is a timeline, right? An example here. So I have an active object store. I got these 4 files that's captured in the snapshot. And your active object store is always moving, right? So in between, what can happen is your 9, 11, 13, and 15, they can get compacted into 17, 19, and 21. And new updates are coming to new files. See, it's messing up your whole logic of how, how to look at just the newly created SST files. Again, something similar happened here. So what we do is we track it with the help of a DAG that we get as we get different kind of event notification from RocksDB. So this is an actual DAG from one of the actual runs on a very small data set. So initially, let's say at the top level, your RocksDB directory, it contained 9, 11, 13, and 15.sst. This is the time when you took a snapshot 1. And then, RocksDB compactions happened in between. The new changes also got applied. So let's say eventually you are at this stage, which is showing as snapshot 2 in the picture, right? And then you want to compute diff between them. So all we do here is we do the DAG walking with the initial set of nodes, that is 9, 11, 13, and 15, right? And whatever nodes that get left out, those are the nodes that contain the diff. We can go through those nodes, those SST files, and then we can very efficiently calculate what has changed between them. And of course, there are like other details also, like how do we track renames and things like that. So for that, every key has a unique key ID that does not change across rename. Using that, we can track it. But overall, like this is the framework that we use for efficiently computing our SnapDiff. I guess that's all I have. I have a demo. Can we? Oh, we can't click on this link. Can we? So can we go to, little fast forward? Yeah. So here we are just creating some content here. Yeah. Fast forward. So in Ozone, I'm creating a volume here. Yeah. We created some buckets. We are putting some keys. Yeah. And this is where we create the snapshot on this bucket. And we are listing the snapshot. Then we will create some churn after creating the snapshot. Yeah, fast forward. We are just creating some churn. Yeah, some more. Then we created another snapshot after creating the churn. And then, yeah, some more. Yeah, we show the SnapDiff API. Yeah, of course, it's asynchronous. Eventually, it will return the result. Yeah. Yeah, that's all I have.
Hello everyone, my name is Akanksha Mahajan and I'm a software engineer in RocksDB. Today I'm going to talk about the optimizations that we did in prefetching for scans. Today I'm going to cover two topics. First is a basic overview of prefetching in RocksDB and another one is the optimizations that we did. So internally we have high latency storage and we wanted to reduce the disk read latency impact on overall scan latency. That motivated us to do some optimizations in prefetching so that we could reduce the read amplification and avoid unnecessary IOs. So RocksDB does enable automatic read ahead size whenever it notices more than 2 IOs on a same table, as we can see above the diagram, unless users specify it explicitly through read options, in which case we start prefetching from the first miss. And the buffer, the prefetch data is stored in buffer, which is maintained by file prefetch buffer class. So whenever there is a miss of data block in cache, RocksDB call file prefetch buffer to get the data. If the data is there in the buffer, it returns the data from the buffer. Otherwise, it calls underlying file system to get the data, along with additional read ahead size. More information about the read ahead or its parameters, you can go through the link mentioned below. So to enable these optimizations, you have to enable the auto read ahead size option through read options. And we recommend it only for forward scans, because if RocksDB notices any backward scan like prev or seek for prev, we internally disable it. And along with the auto read ahead size, you have to specify the iterate upper bound as well as the block cache. So the first optimization is to prefetch till iterate upper bound. User can specify iterate upper bound through read options, and RocksDB makes sure that it doesn't read any data beyond that iterate upper bound. So in this case, RocksDB makes sure it doesn't read the data beyond data block n. However, there wasn't any constraint in prefetching, because of which, let's say if there was a miss for data block n, File prefetch buffer would call underlying file system to get the data block n, along with additional read ahead size, which isn't needed in this case, but we were doing an unnecessary I/O. So we added an optimization to add that restriction. As a result, we are saving that I/O. Next optimization we added is to trim the read ahead size by looking through block cache. So we provided the support for both sequential as well as async I/O. For sequential scans, let's say these are the data blocks with the offsets mentioned in the diagram. And there was a miss for data block with the offset 100. File prefetch buffer, as usual, will get the data along with the additional read ahead size. So let's say the end offset is 350. So with the optimization, it will call the block-based iterator, give a read callback to that. And the block-based table iterator will look up into the cache and store the information. So as we can see that 250 and 300 data blocks are already in the cache, so we don't really need to prefetch those. So block-based table iterator will update the end offset to 250. And as a result, file prefetch buffer will only prefetch from 100 to 250. And we are like saving the I/O by reducing the read size in this case. Same is if it iterates and there is a miss for 350. So the process will be the same. We already have 550 in the cache. So file prefetch buffer won't read that 550 data block, and the updated offset to prefetch and offset will be the 550 in this case. For async I/O as well, the process is the same. It's just that it maintains two data buffers, two prefetch buffers. And we can think of second buffer as an extension of first buffer, which reads the data asynchronously. So for the first case, there was a miss for 100 data block at 100 offset. So the process will be the same. It will only prefetch 100 till 250, and 250 and 300 data block will be read from the cache. And since we have two buffers, so second buffer will go asynchronously to read the data. And for that, file prefetch buffer will call the block-based table iterator again to get the updated offsets for the buffer 2. As we can see that 350 will try to trim the read ahead size from the beginning as well as from the end. So we can see that 350 is already there in the cache, so we don't really need to read that data, as well as for 500. So prefetch buffer, block-based table will update the start and end offsets, and we are only prefetching from 400 to 500. So we can see in this example, we are not prefetching the 250, 300, and 350 data blocks. So once the first buffer is consumed, we'll send it again to further prefetch the data. And the process will be the same. It will start from the next offset, which is 550 in this case, and the end offset will be 750, and it will only prefetch 600 till 750. So we did some experiments internally on scan-heavy tiers, and we did see that the prefetching discards that we don't really use, like which get discarded, reduced from 13 to 1.2. And we saw reduction in the reads as well. We are rolling it out in the production as well. So I wanted to thank my team members, Anand and Peter, who helped me in this project, and my manager, Danny. Thank you.
Hello everyone, I'm Frank from University of Washington. Today I will talk about Dremel, adaptive configuration tuning of RocksDB key value store. This is a joint work with University of Washington and University of Wisconsin-Madison. Persistent key value stores are widely used, and a bunch of applications such as database systems, object storage, stream processing, and so on. Before my talk, I think lots of folks from industry already described their practical usage of RocksDB in their production. However, tuning RocksDB to achieve high performance is non-trivial, and there are several challenges around it. First, the challenge is about massive configuration space. For RocksDB, it has tens of important knobs, as this example shows. And what's worse, for some parameters, they have continuous range rather than discrete value. For example, for memory buffer table, and it can increase from several kilobytes to several megabytes. It is a continuous range rather than discrete values. So configuration space is very huge. The second challenge is that there is fundamental trade-offs for RocksDB. We did a simple experiment here. We randomly sample hundreds of configurations and run RocksDB and collect metrics. This figure shows read and write latency. As this figure shows, for some situations, we cannot improve one dimension without hurting the other one. It means that there is inherent trade-off for read and write performance. So tuning systems have to navigate a good trade-off between read and write and between different operations. The second thing is that we notice that there are a bunch of parameters and configurations which are not on the optimal curve. It means that tuning system should filter out some suboptimal configurations which are not on this orange line. Third challenge is that, as Danny mentioned, that RocksDB is designed to run over any workload and any hardware. So we should adapt to the different hardware and different workloads. However, it's a challenge that because different storage medium have very different characteristics. For example, for SSD, for HDD, or cloud environment, it's very different. And also for workload, they are read intensive or write intensive, and also read and write could have different mixture ratio. Here we have one experiment, and I set up slow and fast SSD, and also set up read intensive and write intensive workload. Combined, we have 4 scenarios. For each scenarios, we set up 4 configurations. From this experiment, we can see that no single configuration is always best. It means that we need to adapt the configurations for specific workload and specific hardware. Fourth challenge is about tuning time. It's very expensive in terms of evaluating each configurations. Because RocksDB metrics like IOPS or latencies, we need to wait for several minutes, even several tens of minutes, until the metrics going stable. And then we can query the stable results. For each configurations, generally, we need to replay the trace and collect the metrics. It means that if we have hundreds, thousands of configurations, for each configuration, we need to replay the trace, collect the metrics. So it's very time consuming. So far, we have visited 4 challenges. And in this work, our goal is that we try to quickly identify configuration that achieve high performance while adapting to specific workload and hardware. Let's see how to achieve this. Before describing our solutions, let's quickly review the underlying data structure of key value stores. It's very important for performance tuning. And I think before my talk, and lots of folks already cover this topic, and I'll just quickly walk through it. RocksDB, like other key value stores, and they adopt the LSM tree. For LSM tree, it contains two components, memory component and storage component. For memory components, it has several tables. For memory tables, it is used to buffer recent update, and for block cache, it is to serve the read request. For persistent storage, there are a bunch of SS tables. SS tables are files of sorted key value pairs, and SS tables are structured as a series of levels from lower level to higher level. For LSM tree, 2 basic request types. First one is write. For write request, memory table firstly absorbs it. When memory table is full, and it leads to write store. And the memory table will be turned into the immutable memory table, and immutable memory table will be flushed out. When lower level, like level 0, is full, and compaction will merge lower level access tables into higher levels to make empty room. For read request, it firstly queries the block cache. If a cache hit, and then it will return the results. If the cache miss, and it will query several access tables in the storage component. This is the background of the LSM trees. Configuration tuning essentially is to play with performance factors which affect the read and request performance latency or IOPS. LSM tree is split into two components, memory and storage component, and we have two basic read and write request types. For write to memory, the key factor is write buffer full frequency, because when write buffer is full, and user I/O will be blocked, and performance will be affected a lot. So the key factor for write to memory is write buffer full frequency. For write to storage, compaction frequency is important, because compaction is a major way to write data to the storage and also update the storage components. How frequently compaction happens could affect the performance a lot. For read request, read from memory, the major factor is block cache. If block cache hit, and the read request will be returned, and there's no need to query the access table from persistent storage. For read from storage, and read access table cost is important, because read access table is the only way to access the storage component part. Here, we have very important observations that we only have 4 abstract parameters or performance factors, which is much less than original parameters. Abstract factors are only 4, which fewer than configuration role parameters. Given the observations, we have several key ideas. The first idea is that feature fusion. We have one insight. To handle massive configuration space, we can fuse a large number of role parameters into a small number of fused features. Then, we can tune configurations over fused space rather than original space, and then parameter space can be reduced significantly. Question is that how to fuse role parameters or how to fuse the role knobs into abstract performance factors. As we know, machine learning model is really good at learning functions. How about training a machine learning model to learn functions and use ML to do search mappings? We indeed try the machine learning models. Unfortunately, it cannot work well. There are several reasons. First reason is about the data collections. As we know, to get a good machine learning model, we need a lot of training data. Especially for massive configuration space, we need a huge amount of machine learning data to train. For storage system, it's very expensive. For each data point, we may need several tens of minutes to query results and to collect the metrics. And we have hundreds of thousands of parameters and configuration space to tune. So it's very expensive to collect the data for machine learning model. One prior work run RocksDB continuously for 6 months to collect data. Even though we have this data, the second problem is that it's really hard to be general for varying workload and hardware. Even we have the same type of hardware and we collect the metrics for this hardware. If the read and the write ratio change, the RocksDB behavior will significantly change. It means that the data collection we get may be applicable to the new hardware or new workload things. The third problem is poor interpretability. For machine learning model, especially for the black box model, it's really hard to know how to involve parameters or which parameters are involved. I think these problems are still big problems for machine learning community. We are thinking if we can use some alternative method to do this. We select closed form expressions. What is closed form expression? For example, for compaction frequency, if we can calculate it with a closed form expression like this, and then we can encode a bunch of parameters into one. At this point, we can discard the mathematical details, and later I will introduce how to derive this compaction frequency. if we have this closed form expression, it's good because we don't need training data to collect to collect, and we don't need training data to get a machine learning model. The second thing is highly interpretable because we can clearly say which parameters are involved and how to involve these parameters. The third thing is that when we derive these expressions, we use our domain-specific knowledge. For example, RocksDB and architecture-related knowledge to derive these parameters. It means that our knowledge can be general for different hardware or different workloads, and then it can improve the generality for our expressions. Next, the key question is that how to derive these expressions. We have several principles to guide us to derive. First one is that it should be independent of workload and hardware-related parameters. By doing this, we can simplify our process to derive. We don't need to care the workload and hardware so far, and later I will describe how to handle the different workload and different workload and hardware things. For derive, we just consider RocksDB-related parameters. The second principle is that we apply asymptotic worst-case analysis. Lessons from algorithm analysis. Worst case is always deterministic and bounded. It means that worst case can provide the IO performance bounded analysis. The third principle is that we try to encode as much as possible asymmetry domain knowledge into our fusions. It can improve our generality to derive the closed form expressions. Here, I directly give the final results for the expressions, and you can check our paper for more mathematical details. The first key idea is feature fusion. With the feature fusion, for each configuration, we have 4 features, and we use 4 features to represent the configuration things. Next step, if we can represent each configuration with 4 features, and how do we decide, or how do we identify which configuration is the best? To adapt to different workload and different hardware, we use online tuning method. In this setting, we apply the multi-arm bandit model to identify which configuration is the best. For multi-arm bandit model, there are several concepts. The first concept is arm. In our setting, each arm is a group of configurations. The second concept is arm pooling. To pull the arm, we sample configuration from each arm and then run these configurations and collect the metrics. And in terms of multi-arm bandit model, we call it as arm poolings. Similar to other multi-arm bandit problems, our problem is how to identify the best arm. In other words, how to identify the best configuration. To quickly identify the best arm, one naive or straightforward is that we can run the entire workload for each sampled configurations. But as I said before, it's very expensive in terms of time cost. Here, we take one approximation strategy named as successive halving. We run the workload and configurations, but we don't run the entire workload for each configuration. At some time point, for example, for 60 seconds, we perform early stop for the worst half, and at 80 seconds, and we perform this early stop again. At each time point, we throw out the worst half. By doing this, we can reduce the time cost in total. So far, we have described the 3 key techniques. The first one is feature fusion. The second one is bandit-based online tuning. And the third one is approximate quick evaluations. By combining these techniques into one workflow, we get the Dremel. From the Dremel workflow, we can pick the best arm or best configurations from a from massive configuration space. Next, I talk about some evaluations and results. Because the Dremel and the RocksDB can adapt to different workloads, and we use a synthetic workload like YCSB, and we also run some real-world workloads. For different workload, and we set up read and write mutual different, and set up the different key distributions. To simulate the different hardware conditions, we rate limit SSD bandwidth and to get different bandwidths for SSD part. And we also simulated two adaptive scenarios. The first one is initial configuration. It means that the configuration is without preloading data. The database is 0. The second one is the adapt on the fly. The database already has some preloading data. We have two scenarios. Dremel can be used to optimize a bunch of metrics. In this evaluation, we focus on IOPS and latency. In this experiment, we compile Dremel against the Bayesian optimization method, random search, and expert experience. Here, expert experience is from the RocksDB wiki tuning guide. We can see that with the same tuning time, Dremel can find configurations that achieve higher IOPS than other methods for different settings. Here, I show the 6 settings, and Dremel can achieve the best performance. In second experiment, with varied time budget, we can see that the Dremel can find better configurations faster. And also, we notice one point. For Dremel, it requires minimum time budget because we need at least pull each arm once to make decisions, and this is why the Dremel requires minimum time budget. Third point is that if we allow the Dremel more time budget, and then we can pull each arm multiple times, and the Dremel can find the better configurations. In our paper, we have more evaluation results. Besides IOPS, we also try to optimize other metrics like latency and also memory usage, also storage usage. And we break down the whole system into different components, like the feature fusion part and also approximation part to give more results. Please check more details in the paper. In summary, we investigate 4 challenges while tuning RocksDB, and also we propose some preliminary results and also characterization results about these challenges. For Dremel, we design a configuration tuning system. It can quickly identify the configuration that achieve high performance while adapting to specific workload and hardware. Evaluation results show that we can achieve better end-to-end performance with less tuning time and more flexibility. Thanks for listening, and if you have any questions, feel free to contact me. Thanks.
All right, we actually are ahead of schedule a little bit, so we also have time for questions. If we can maybe have like approximately 5 minutes of questions, and then we can have pizza. Yeah, and for any of the speakers that just went the last 3 talks.
Hey, this is for Dremel folks. Does it work on any config systems or just the RockDB? Sure. Okay. So does this work on any key-valued systems, or it's just the RocksDB?
Actually, we also try to apply this to other ones. For example, for Apache, and we also try to it.
And how do you compare? Does it work for all of them?
Actually, one key difference for different systems is that we should adjust the parameters fusion part. And for different model, maybe we need to encode different domain-specific knowledge to get the parameters, and then other workflows keep the same.
Okay, cool, thanks.
Yes, it's a good question. Thank you.
Any other questions from the group?
You mentioned that it went into further depth in the paper about tuning for memory, for storage, for IOPS, et cetera. Does that work all in tandem at once for some sort of maybe pre-configured amount of trade-offs, or is this all, you choose to do one thing that you want to optimize for?
Yeah, it's a really good question. Yeah, we indeed try to optimize other metrics. And there's one trade-off here. In our system, we focus on single objective. Because if we have multiple objectives, first the question we need to answer is that how to define a trade-off between the different objectives. Sometimes it's completely decided by users. For example, and users emphasize memory or users emphasize the storage. So I think if users can give one function or one objective or utility functions to describe how to play this trade-off, And then we can fuse the objective into one objective, and then we can play the same systems. Yes, really good questions. Yeah, for the multiple objective tuning things.
Hi, my question is for Akanksha. Is she here? Hi. So nice talk. I was curious, what triggers the read ahead? Because you mentioned how you handle the read ahead, but is there any change in the way the read ahead is triggered and how many blocks you need to read from?
No, there isn't any change in the behavior. It's just the read ahead size at that time we are changing.
Okay, thank you. That's fine. Cheers.
Any other questions? Okay. All right. In that case, let's go ahead and wrap up. Thank you again for coming. It's great to have everyone here. If you didn't already get your swag, please go ahead and get it. We have pizza in the back. There's pizza. Again, there's vegetarian options, so please be aware of that. And just have some fun getting to know each other. And thank you again for coming. I know it's hard on a weekday with traffic coming out here, so I hope this was well worth your time. I will send out a survey offline to the Meetup group. If you guys are able to just fill out the survey and get some feedback on what worked, what we can do better, that'd be great. So thank you.